based on that electron configurations, what do you think that probably means? What does the word configuration mean?
Kind of to like shape.
Okay, kind of shape. What else? What's another word we could use to describe configuration? Mm-hmm.
Like makeup.
Okay, good. How it's made up. Good. Another word I'm thinking of is arrangement. Okay, configuration tells us how things are arranged, their placement or their position. And so when we talk about electron configuration, what we're going to start looking at is we're going to examine individual atoms and figure out where are their electrons located. How are the electrons configured around the nucleus of the atom? We've talked a little bit about some older versions of the atom, older models of the atom, like the Rutherford model we talked about, right? Where he had his kind of orbiting around the nucleus like a planet. That's what they thought was happening. And so now we know a little bit more about where electrons sit around the nucleus, okay? And so we're going to start diving into how can we find essentially the address of an electron. We're going to be able to find an address for an individual electron, okay? And we will be able to find an address for every electron that is found in an atom. That's really our goal for the whole chapter, is to be able to figure out where is the location pretty precisely of a single electron on an atom, okay? And we'll be able to figure that what that looks like, okay? So we're going to start back at some initial models of the atom. We talked about the Rutherford model. That was a pretty early model of the atom. Then we moved into something called the Bohr model. And the Bohr model said that electrons circle around the nucleus, but only in really tight rings. It's almost like being on a ladder. You can't be in between the steps of a ladder. You're on a ladder rung or you're on the next rung, right? You know what I'm saying? You can't survive somewhere in the middle. You got to be on one or the other. And so that's really what they said happens in the atom. Okay, they said that electrons can basically just be on these levels, okay? And they called them energy levels. Okay, so they said they're at their lowest energy level when they are closest to the nucleus, and they're at their highest energy level when they get far away from the nucleus. What do you think is the preference of an electron, to be at a high energy level or a low energy level? Low. What's your preference as a person, to be at a high energy level or a low energy level? Some of you high, most of you low, because you try to sleep through my class, okay? So most of you want to be at a low energy level as often as you can. So it's the same thing with electrons. They want to be at a lowest energy level possible, right? To be able to be comfortable. That's what they're thinking of here. Low energy level, okay? Electrons are in their lowest energy state when they're in the orbit closest to the nucleus. So the tighter they are to their protons, the happier they feel, right? The more relaxed and low energy they feel. The farther they get away from their nucleus, it's almost like they get anxious about it, right? They're farther away from their home, so they don't like that. They want to be at a nice low energy level. Okay? So what this model tells us is that an electron can't hang out in the middle. It's got to be on an energy level or on the next one. It can't be in between, right? It can jump, but it can't stay in between, right? That's called the Bohr model. But now we're going to move into something called electron configurations, and that's when we start looking at the arrangement of electrons in an atom. We're going to figure out how are they laid out, where are they located, where do they sit, all those types of things, okay? And so when we study electron configurations, we can study electron configurations in an element's lowest energy level, or we can study them when they are in what's called an excited state. That would mean that there's more things happening. But we're going to start by studying their lowest energy level, and that's called their ground state electron configuration. So we want to study them when they're nice and relaxed and everything's normal and all that kind of stuff. We're not going to throw in a bunch of exceptions just yet, right? That could be what's called an excited state, and we would get to that in later classes. But right now we're going to start with what are called ground state electron configurations. Okay? So in order to do that, I want to give us some parameters and ways that we can identify patterns in electron placement. Okay, there are different places that electrons can be placed. And so I'm going to skip ahead a little bit here to talk. And these pockets of electrons and the order in which they fill into an atom follow a very specific pattern on the periodic table. And so it makes it really easy for us to figure out where is the electron located for this atom, because it follows the pattern on the periodic table. So here's how it works. These two groups right here, the blue, right, group 1 and group 2, are considered S block elements. Okay? So groups 1 and group 2 are S block elements. Okay? This group over here, these 6 groups over here are the P block. Excuse me. This orange group in the middle, the transition metals, are the D block, right? And these are already written on yours, but I'm just showing you again. And then this lanthanides and actinides down here are considered the F block. So let me tell you what that means. Okay, let me tell you what that means. That means if an element is located, I need everyone to hear this because this is a really important part of what we're doing here. If an element is located in the P block, let's study oxygen for a second. The element's located in the P block. That means oxygen's last electron is in a version of a P orbital. That's what it's saying. Okay? If the element is located in that block, then that means the last electron to go into oxygen is found in a P orbital. Okay, do you understand what I'm saying there? Let's walk it back a little bit farther. So how many electrons does oxygen have? How many electrons does oxygen have? Not 16. They have 8. They have 8 electrons. Okay, and so that means if I'm counting out its electrons, 1, 2, 3, 4, 5, 6, 7, I've thrown in 7. The 8th electron has to then be in a P orbital. Okay, in a P orbital. So one of those hourglass-shaped orbitals. Okay, that's essentially what we're looking at here. And so this periodic table pattern gives us a really easy way to figure out where are all of the electrons at. Okay? This is going to seem really abstract and really kind of crazy until we start doing some examples, and then it comes together really quickly. So I want you to hang with me, okay? So if you're not quite understanding where we're at yet, that's okay. I promise we're going to get there, okay? So let's keep moving through our periodic table and breaking this down into phosphorus. What orbital would phosphorus' last electron be in? What type of an orbital would phosphorus' last electron be in? It would be P, but more specifically, what energy level would it be in?
3.
Yep, 1, 2, 3, 4, 5, 6, 7. So it would be in a 3p orbital. Would we agree with that? It's in the 3rd energy level, so we've got 3 levels of orbitals, and it's in a p version.
So then there's 2?
What do you mean 2?
It's in the 3rd.
It's in the third row down that tells us energy levels. What if I wanted to find out what if I wanted to find out calcium? Where would calcium's last electron be located? In what orbital? 4 what? 4s, right? It would be in a 4s orbital, right? Calcium's last electron would be in a 4s orbital.
So it always starts with the S
So
block, and then we
magnesium
build on
S, P, D, then F.
4D.
Right here? Okay, that's a good question, but no. And I haven't taught you that rule yet. Here's why. You were getting it. As far as what I've told you, you've got it. But here's what happens. In the D block, they sit in the 4th period of the periodic table. However, they become available in the 3rd energy level. So what we say is this D row right here is actually 3D. I know.
That changes the whole entire.
That changes this. So let's look at it up on this periodic table. Okay, I know. I don't make the rules. Okay, this is the 4th energy level, right?
So then the row down would be 4?
This would be 3D. 40, 5, and 6, right? So they really have to shift up 1 because they become available in the third energy level. But you can't move the whole periodic table just for that, right? That would throw everything else off. So we have to remember that if it goes, when we fill it, listen, if we were filling our orbitals for titanium, we would fill 1s, 2s, 2p, 3s, 3p, 4s, then we'd go 3d, 2.
Is it because they're in like the pockets or whatever? Like,
Yeah, they're in the pockets, and the d orbitals become available in the third level, not the fourth. So that's just a rule we can't change.
And is it also because of how they're like set up, like here?
Yeah, their shapes. Yeah. Okay, here's one more trick. One more trick. Listen. This becomes 3, 4, 5, 6.
Okay.
These guys down here, they're supposed to fit right here, aren't they?
Yeah.
So it would be 6 and 7. However, this is 4f and 5f. I know. So write those down on your periodic table, okay? Actually, on the next slide, I have a couple slides here in more specific patterns, okay? As we move through the periodic table and as we move through our element, every time we move, this got off a little bit here. Every time we move down on the periodic table, we gain an energy level. And there are 7 total energy levels. So it is similar to that ladder drawing that we saw. Every time we go down on the periodic table, we get another shell, another set of orbitals starts up. And so when we go from the first 2 electrons, once those are full, we add another energy level, and now we've got another orbitals to fill, another set of orbitals to fill up, okay? And so here's how these orbitals break down, okay? The first row or period on the periodic table only has 2 elements in it. And that's because in the first energy level, there is only, if this is my nucleus, there is only an s orbital available. Okay, in the first energy level, there's only one s orbital available, and it can only hold 2 electrons. So now do you see how that corresponds to the first row on our periodic table? It only has 2 elements. It mirrors the fact that it can only hold 2 electrons. So now let's go down a group into the second period. We would add another s orbital, and we would add the p orbitals because there are 2 plus the p orbitals. So every time we go down on the periodic table, we add another level of orbitals that have of spots for electrons to sit. Okay, how are you doing? Are you hanging in there a little bit?
Yeah, how would I write that down?
Yeah, okay. So, yeah, I know, it seems pretty abstract until we actually get there, okay? Let's walk it back. Let me try and say it another way, okay? If I'm looking at oxygen, let's get rid of my drawing here. If I'm looking at oxygen, which sits right here. If I'm looking at oxygen, it has 8 electrons. Would we agree with that? So it's 8 electrons. Its first electron is in a 1s orbital. Its second electron is also in a 1s orbital, right? 1s tells me it's the first energy level, and s tells me the shape of the orbital that it's located in. We agree?
But isn't it in the P?
Okay, yes, that's right. The last electron is, but the first ones that go in have to go into the lowest energy level first. Okay, so as we keep filling oxygen's electrons, the third electron that goes in is in a 2s orbital. The fourth electron that goes in is also in a 2s orbital. That is now full, and so we move on. And we know the next electron to go in, electron number 5, 6, 7, and 8, are all found in a 2p orbital. Right? We have to fill the electrons in from lowest energy to highest energy. So we just fill all of the spots available to us until we get to its last electron, which for oxygen was electron number 8. Right? It was number 8. It would be in a 2p orbital. Okay, yeah, go, Kira.
How many electrons have to be in one of the pockets?
Yeah, it can hold a maximum of 2.
And
So it can be 1 or 2.
goes to the next one.
Then it goes to the next one. But in the p block, right, there are 6 spots. That's because there's 3 versions of the p orbitals. So we go like this one, 1, 2, 3, and then we fill our second electron, 4, 5, 6 for each one. So we'll get to that, how that looks when we actually put it in there, but we'll keep going, okay?
So the last one doesn't have to be full of electrons?
The last one doesn't have to be full, no.
It's just there.
That's right.
It could be
That's
full.
right. Could be full, could not be full. Okay? Let's go back to some basic questions here. If I want to look at written for you.
Abbreviated.
Okay, see how in this one I have them written in there for you?
I see. Wait.
Okay? 3D, 4D, 5D, 6, and then 4F, 5F. So they shift a little bit about when those orbitals become available.
Doesn't that go in the
Okay?
back too?
Say it again.
Doesn't these two go?
Yeah, they fit right here, so they're really,
So how are they not 6 and 7?
I know, the F orbitals become available in the 4th energy level. Yeah. So I have it written on this slide for you. Have them all written out. Do you see that? Okay. I'm going to give you one more. Stop. Listen. I'm going to give you one more piece of knowledge about how to figure out what orbitals get filled in what order. Because that's really what we're doing. We're throwing electrons into the correct orbital in the correct order. Right? We've got to put them in the right spot, but they have to always fill from bottom to top. So I've got one more way that you can use to help figure out how the orbitals come in order. I like to just go by the periodic table, and I fill the 1s orbitals, then 2s, then 2p, then 3s, 3p, right? That's what I like to do, but some people don't like that as much. It's about an orbital. Okay, so we'll go back and look at the last few slides here in a second, but we're going to skip ahead and talk about an orbital, okay? An orbital is essentially an electron pocket, okay? I want you to write that in. It's an electron pocket. You know, are we good with that abbreviation being for electrons? E with a little minus sign is how I write electrons. Okay, an orbital is an electron pocket or an electron holder, okay? Individual orbitals, I don't know how I said that. Individual orbitals can hold 2 electrons. That's important. Individual orbitals can hold 2 electrons. But there can be multiple orbitals around our nucleus to help hold all of the electrons that we need. Okay, so let's go back to beginning here. So we're not really looking at our ladder situation anymore. Now we're going to examine this newest theory of the atom called, they call it quantum theory. Okay, and so we're going to start looking at where electrons are located. And we know they sit in these orbitals or electron pockets. Okay, there are 4 types of orbitals, 4 categories of orbitals. There are s orbitals, p orbitals, d orbitals, and then one final kind called f orbitals. So 4 categories of orbitals. And each of the orbitals takes on different shapes. Okay, so the s orbital is just a circle. It's just a sphere. Okay, and the first electrons that go into every energy level go into an s orbital. Okay, I'll walk you through the patterns here in just a second, but the first 2 electrons to enter an energy level have to go into an s orbital, and then that s orbital becomes full. Then we move on to a p orbital, and p orbitals are shaped like this little, hourglass. I don't know, yeah, that's a good way to put it. There are 3 versions of p orbitals, so if they can each hold 2, and there are 3 versions, how many total electrons can p orbitals hold?
3. 2.
There are 3 versions, and they can each hold 2 electrons. So 3 times 2 is 6 electrons. So a total of 6 electrons. This one holds a total of 2 electrons because there is only one version of the s orbital. Okay? Let's move into the next category. The d orbitals have 1, 2, 3, 4, 5 versions. Look how crazy those shapes are. Like little clovers. This one right here is what they look like if they all overlap at the same time. So those electron pockets look crazy, right? Okay, but there are 5 versions of the d orbitals. So how many total electrons can fit in the d orbitals? 10 electrons can fit total in the d orbitals. And then the f orbitals, I don't have a picture of those because they get even more crazy. There are 7 versions of the f orbitals, and so they can fit how many electrons? 14 electrons, right? Because each version can hold 2.
What's the one in the bottom right?
This one right here, that's one of the 5 versions of the d orbitals. Okay, so it just looks a little funny. So if you put them all together, this is what they look like.
Are they together most of the time?
Yeah, they're always together. Yeah, they'll always be lumped together. And like these are obviously invisible pockets, right? We don't actually see that. The way we know that the pockets are this shape is we've done like a lot of experiments that almost make a scatter plot of electron placements. And so that you see this little cloud and they see, oh, this is kind of the shape that they make. And so it kind of gives us some definitions. But these are all very gray lines. Does that make sense? It's not like there's an actual physical pocket, right? These are all just areas of like electron clouds. Okay. Okay, so do we understand what an orbital is? It's an electron pocket, right? And there are 4 different categories of orbitals: S, P, D, and what's the last one? F. Okay, good. Let's go back to the periodic table then for a second. So you might use this little cheat sheet, okay, which that's what I printed for you. Okay, this little shortcut sheet, electron configuration pathway, I call it, boys, thank you. I just call this the pathway. You start with the 1s orbital, you fill it up, and you go to the 2s orbital. You fill it up, go to 2p, then 3s, then 3p, then 4s, 3d, right? If you follow the line, it tells you the order in which they need to be filled. I don't like the pathway as much as just using the periodic table, so I'm going to leave that up to you, which you prefer. Okay, but I printed this big for you in case you like it. But this shows you, if you follow the line, what which orbital to fill next. Is that I start with 1s, I follow the line, next comes 2s, then 2p, then 3s, 3p, 4. It only gets like helpful when you get up here. 6s, 4f, 5d, 6p, 7. You know, it gets helpful when you get up really high. But for the initial ones, I think it's easier to just follow the periodic table. Okay, that's my preference. Okay, are we ready to try some more? Okay, let's try some practice here. Okay, let's try some practice. And I don't even know that I want to use this sheet. I'm just going to go blank sheet here, okay? So, when we write our electron configuration, we have to account for every electron that's there, not just the last one. We have to account for every electron. So I want to start with carbon. Let's look at carbon. Okay. Carbon has how many total electrons? 6 electrons. And we know its last electron will be in what type? Carbon's going to be where?
The second.
Second. So it's going to be 2p is where it's going to end. So we need to fill every orbital that comes previous to that. Okay, so we have to fill. This is how we write our electron configurations. Okay, just watch and listen, please. We know that the 1s orbital can hold 2 electrons. Okay, that's how it gets written. 1s orbital, and then up kind of as an exponent, we write how many electrons are present in the 1s orbital. We have to fill that in order to jump down to get to carbon. Would we agree? Right? We have to fill that first energy level in order to go to the second, because that's where carbon's electron is located. So we fill that one up. After we fill the 1s orbital, we jump down, and now we work on the 2s orbital. And so 2s orbital is also full. It has 2 electrons present. Do we agree so far? Okay. We're following along on the periodic table. Boys, please. We're filling all of our orbitals before we can get to 2p, because we know our next one that comes along, right? 1s, 2s, We're going to slide over here. Here's our 2p orbitals right here. And where's carbon located? It's which element? 1, 2. So we're going to go 2p2. There are 2 electrons located in that p orbital.
So what makes nitrogen be 2p3?
Okay, the shift comes from the fact that the d orbitals become available in the 3rd energy level. So we don't relocate the whole periodic table just to show that trend. That's just one we have to remember. So if we don't get to the d orbitals, then nothing changes, right? We don't have to make any shifts. Okay, so let's check our answer here. We said carbon has a total of 6 electrons. 2 of them are in the 1s, plus 2 more are in the 2s, that's 4, plus 2 more, so that gives me a total of 6 electrons. Do we agree? So you can always check your answer to make sure you've got all of your electrons accounted for. How many total can the p orbitals hold?
2.
Okay, no, there's 3 versions. So how many do we say they could hold total? They can hold a total of 6. So let's look at fluorine now and see how its electron configuration is different. Okay, look at fluorine. Fluorine's last electron is going to be in what type of orbital? Is it also going to be 2p? Yeah. Okay, but I have to fill the previous orbitals first. That's right. I have to fill the previous orbitals first. So I would have 1s and 2 electrons are there because it has to be full.
And then 2s.
2s. How many electrons are in that orbital? 2, because there's just one version of the s orbital that can hold 2. And then we get to 2p, and fluorine is number, look, in the orbital, fluorine is 1, 2, 3, 4, 5. So 2p, 5. Then I add up my electrons. 4 plus 5 gives me 9 electrons. Is that how many fluorine was supposed to have? Yes, right? This is not part of my answer. This is my answer. That's my electron configuration, right? That is the arrangement of my electrons within their orbitals.
Will we eventually do like cat ions?
We can, but those are a little tougher to figure out. Are we looking at fluorine, or are we looking at oxygen -1, right, with an extra? Those are harder to see, but we can still do them. Yeah, that's a good question. Yeah, Calvin.
So what are we actually like finding out?
So what we're doing here is we're giving like a map of where the electrons are located. In fluorine, the first 2 electrons that go in are in the 1s orbital. The next 2 electrons that go in are in the 2s orbital, right? We filled it up. Now we have to add another shell, a 2s, and that's where they are. And then the next 5 electrons are found in a 2p orbital. So we've got this kind of basic map of where our electrons are located. That's what we're trying to do.
So is the F block the most unstable since they're not as close?
That's right, they're far away. We will eventually get more specific and give an individual electron its address, but for right now, we're just giving ourselves a map. Okay? Okay, let's try sodium. Sodium is Na. Back so we can see the examples we already did. Sodium is Na. How many total electrons are we going to need for sodium?
11.
We're going to want 11. So I'm just going to put that over here as a reminder. Okay? But I always have to start by filling the prior orbitals. So I fill my 1s orbital with 2 electrons. I fill my 2s orbital with 2 electrons. My 2p orbitals, how many can they hold? 2p, 6. So I've filled all the way through what element so far? I've filled through what element? Neon. I filled through neon. And so now I'm going to come down here. And what's my next element?
3s.
What'd you say?
3s.
Sodium? Oh, 3s. I'm sorry. Yes. Yes. You're right. So my next orbital is the 3s orbital. And so how many of sodium's electrons are found in that 3s orbital?
Sodium?
1.
Only 1. Because it's the first element in the block. Right? It's the first element. This would be 3s1. This would be 3s2. 4s1, 4s2. 5s1, 5s2, right? But we have to fill everything that comes previous to that. Okay, is it coming together now that we're seeing examples of it?
Yeah.
Okay, the important part is that Okay, let me ask this question. Do you like just moving along the periodic table, or do you like using the pathway?
Pathway makes sense.
The pathway, I don't really like it. That's that little diagonal diagram I gave you. Yeah. You can follow the line, and it tells you what orbital order to go in. I don't think it makes any sense either, but some people like it. What this one is telling you, listen, what this one shows you. All right, let's try the electron configuration for iron. Iron. Fe. Iron. Okay, how many electrons have to be in my iron diagram? 26 total electrons. We didn't check sodium, but we can. Okay. And what orbital is iron's electron going to be in? Its last electron is going to be in what type of orbital? 3D. It's going to be 3D. Okay, so yes, let's fill everything previous to that. 1s2, 2s2. What orbital comes next? Follow along on your periodic table.
2F.
Nope.
2P.
2p. And they can hold how many? 6. Then we're to the neon already, so we jump down. Now we're at 3s. How many? 2. I'm going to fill it up. Now I slide over. What comes next? No, I slide over. 3p. How many? 6. So now I'm to what element? Listen. If I'm finished with 3p6, I'm like at argon, right? I've put in 18 electrons so far. Now I jump down to potassium, which is 4s2. We're almost done. Now we're at 3D. How many? 3D. 1, 2, 3, 4, 5, 6. There it is. Okay? So we follow along on our periodic table. When we get to the end, we have to start over with a new s orbital, right? When we get to the end, when we get to a noble gas, we have to start over, right? We come down to the new row. Okay? Then you count 2, 4, 10, 12, 18, 20, 26 electrons. I've got all my electrons accounted for. That's what I wanted. So just because the d orbitals become available in the third energy level, but we don't shift the whole periodic table to show that. So you have to just remember that when you get into your d orbitals, they're really one level ahead. But we don't fill them. Listen. We don't fill them in that order. We don't put the d orbitals right here, right? We need to put the d orbitals where they go. We don't just do 3p, then 3d, right? We fill them in the correct order. However, I will tell you that sometimes, like on CK12, it will put them in that order and still consider it correct, and that's okay. Okay, sometimes it'll put all the 3s, in that order, but we don't usually do that. Okay, I want you to try this next one on your own. I want you to try arsenic, AS. Give me the electron configuration for arsenic. 14 total. Arsenic is AS over there, number 33.